Okay, welcome here. So it's our great pleasure to have Kuansan Wang. So he is actually principal researcher and managing director of Microsoft Research Outreach. And we have a wonderful meeting this morning and learning there. They actually have the agent, a machine, go to read millions of articles, and they almost reach like billion article level, so that agent will become really intelligent. And what they hope is this agent could be able to answer some scientific questions in the near future. So we are living in the data and AI time. So exciting that we don't know what will happen in 2 years. So maybe in 2 years you will have an agent from Microsoft be able to address some questions that you don't have time to answer for your PhD student, but the agent can become their second supervisor whatsoever. Anyway, so Microsoft academia search has a lot of data. Recently, they just released 170 million articles to the public. So if you claim or you complain that you don't have the data to analyze, this is the place you should go. And they are creating knowledge graph on this. So a lot of interesting stuff. So now let's welcome them.
Thank you. Thank you for the kind introduction. It's really my pleasure to be here, and this is my first time in Indiana. So it's in Seattle. We are already cloudy and everything. That's why Starbucks is putting the pumpkin latte out already. But it's really nice to see the sunshine. And as the Professor Dean mentioned, today I'm here to share with you a 2-year-old project that we have been doing at Microsoft Research. It's actually quite a trendy topic because this is what I read on the way here. You probably heard that recently there's a new buzz coming back about artificial intelligence and its role in our society, so on and so forth. And for some reason, this wave of AI is not new. In fact, this is the 4th reincarnation of AI. It has suffered 3 different times of down cycles. But for some reason, this time, there's something different about this wave of AI. And it raised a lot of alarm bells. You heard about the Elon Musk and Bill Gates, even Steve Hawkins talking about we should start regulating AI and so on and so forth. That's one camp. On the other camp is Mark Zuckerberg and all these others say, no, that's not real. So this is actually the article just published last week in World Economic Forum. Basically, it asks the question that since the Industrial Revolution, machine has been replacing jobs replacing humans on the jobs. So why this time are we worried? Well, I tend to agree. So my personal opinion is I agree with the finding of this, the description of the article, because this wave, we actually touch the sanctuary area for humanities. It's in terms of cognitive capability. So we probably are not surprised that machine can do better than humans in many areas. Even in the animal kingdoms, we know many other species are better than human in hearing, in vision. Echolocating bats are much better than us in hearing sounds. In vision, all the the birds have a much better vision than us. But in the animal kingdoms, human is the only one that has developed a very sophisticated language and writing system where we can actually document the knowledge we accumulate for the lifetime and then pass it on to the next generation. So in terms of the knowledge gathering and making it as a heritage, it's unique human. But this wave, what we see of AI is that machine is actually taking over this kingdom as well. So specific what today I would like to share with you is the area of intelligence behavior, which we call cognition capability. Right, so the dictionary definition for cognition is the mental process of gathering knowledge, either through inference or through the learning process. And if you think about the everyday notion, we say this person is smarter than the other part in terms of cognition. Typically, you are talking about 5 aspects of the behavior. The first one is computation, how quickly you can respond. The computation typically involves either numerical calculation or logical inferences. If somebody can do a lot of arithmetics in the brain and then talked about numbers very amazingly, we see it actually is certain some intelligent behavior, right? The second one is memory. We know that memory, we accumulate knowledge, but if we don't have memory, then knowledge won't stay. So memory is actually another important aspect. There's a very famous article about human memory. It's called the magic number of 7 plus and minus 2. So it turns out that a lot of intelligent humans, they are intelligent because they actually seems to have a larger capacity in processing the information. So memory definitely contributes to intelligent behavior. The third one is attention. This one is probably very straightforward. You know, a lot of kids, they cannot learn because they are suffering from attention deficit syndrome. So attention definitely is important element for us to learn and to acquire knowledge. And finally, endurance. You can have enough attention, but if you can only sit tight for only a few seconds, that is not going to help. All right, so endurance is yet another one. And then sensing. Typically, we find people that, you just don't, you're missing something, you don't get me. That's because a lot of time our knowledge is passing on, or signals passing on through also those senses. It's not just one single modality, right? So if you go back to look at these 5 aspects of cognition capability, it looks like humans are doomed, because these are the areas that machines are designed to perform better than human. In terms of computation, can you compute faster than the computer? Memory, we have made computer to have perfect memory. Everything it reads, it never forgets, right? And it won't degrade. It won't make wrong association. Attention, I'm sure that my agent won't be distracted by Facebook posts or Twitters. How many of you can say the same thing? Endurance, while I'm speaking here, my machine back home continue doing what it's told to do. It doesn't take a break. It doesn't sleep. It doesn't need to, do all sorts of things that we need to do, right? Endurance. Sensing. My machinery actually is piggyback on the Bing crawler. It's a web crawler to read every article coming online. So if there's a new article on the web or new trends in the world, who do you think discovered it first? Other than the author of that material, it's probably my machine discovered it first. So if you just think about the traditional way of defining cognitive capabilities, it looks like we're doomed. All right? So, but fortunately, the machine has a wonderful thing. Right now, it basically works the way we told it to work. So based on this observation, the question we are asking is, can we actually harness this super cognitive capability the machine has to help human, to make us more productive? And to what extent can we push the boundary so that one day we can actually become better than we are today through the assistance of by harnessing the power of machine. The similar work, you will find amazingly, the similar framework is similar to AlphaGo, the DeepMind's work to teach machine to play Go. The only difference, really, if you look at the architecture and everything, the major difference is the objective function. In the Go, the human and machine are in a competitive mode, whereas in this one, it's in the collaborative mode. and just flip a sign there, it changes everything. So let me share with you a quick overview to what we have done. So the idea here is we wanted to train, as Professor Ding mentioned, we want to see if we can create a super scholar in the sense that this agent just keep reading all the new scholarly publication on the web and educate itself, acquire knowledge by itself. And through the process of acquiring knowledge, it teaches itself to read better, to understand more. So that's the question we're asking, is this possible, right? So like I mentioned, we at Microsoft, we are very lucky that the company actually operates a web crawler. It crawls the webs every 2 weeks. Every week we have tens of trillions web documents down there. We train this machine reading to scan through the tens of trillions web pages and make a classification to say this is scholarly data or not. Our Bing partner cares about a lot of consumer-oriented information, whereas we, in the Microsoft research, we care about material that is useful. They are more useful to us, the scholars. So we narrow it down from the tens of trillion web pages into roughly a billion, slightly more than a billion web pages. And from that 1 billion pages, we identify roughly 170 million unique articles. So a lot of papers appear on webs multiple times. We are able to actually conflate them together. And then once we identify these hundreds of millions unique papers, then we dispatch the deep NLP technology to read them. So for this, for each article, we want to understand what concepts are being described. Are they, so which fields are they, what methodology they are using, so on and so forth. And in the meantime, we would like to know who wrote these articles and which organizations are sponsoring this, right? And so basically the way we model the knowledge is in terms of something we call entities. These are the people, organization, the concept, and in terms of that, like that. And these are the nodes. And then these nodes inevitably have a relationship with each other. This paper is about this concept, apply on this concept. It's authored by these people, published in this venue. So all these nodes actually have a relationship with each other. So that relationship, we model them as links between the nodes. And therefore, the outcome of the machine reading is actually a graph. It identifies this paper has these entities and their relationships as such. And then you aggregate all this massive amount of entities through all the publication together, and it ended up as a gigantic knowledge graph. We dispatched the graph engine index technology to make the search about this entity and relationships very efficiently. And this search is an interface we expose so human can actually query what the machine has learned. But in the meantime, that indexing, the search capability is also used by the machine reader itself. So it can actually more efficiently to leverage what it has understood before to parse what it hasn't seen before, right? So it's actually a feedback loop. So this is a architecture, basic architecture. And the interesting part is that we are actually do this in open. So I'm here today to tell you every stage of the intermediate outcome where you can find them. And we invite you to take a look at it and see if you can build on top of it, right? So this is academic, and in fact, this machine reader actually inevitably would catch up some news article about scholarly achievements. So there's a part of the news, but today's focus will be talking about the paper part. Paper part is actually tends to be long tail. One concept probably is only mentioned in one paper, whereas in the news, the same events can be actually described in multiple articles, and that's actually an easier part to understand. So the research here, we actually want to go into the long tail, where you have a sparsity problem. You have a data sparsity problem. So the machine reading to generate the knowledge graph, and this graph is what we call Microsoft Academic Graph. It's available online. You can download. Just go search Microsoft Academic Graph out there. This is the data sets that mentioned. I'm going to give you more statistic as how big this is and where it is done. And then the knowledge index, after you index the graph, there's a search API that you can use. So this is called Academic Knowledge API. It's available on Azure as a REST API, so you can actually query. It has a HTTP, you do the REST API to query it. You can grab a part of the subgraph or get some knowledge out of it. And then this is actually a REST API. You have HTTP call in, it spits, it gives you back the JSONs. It's not very human readable, human friendly. So we actually put a HTML front end to it. It's that's the Microsoft academic site. It's academic.microsoft.com. It looks like a search engine, but I'm going to tell you how it is a little bit different from the search engine you comes to be familiar with. All right, so quickly going into the underlying machine reading technology, it's the core, the NLP thing. It's basically teaching the machine to do natural language processing. The system, the bulk of systems building on the traditional NLP models, and we are in the process of moving towards a new set of technology that based on deep learning. But from our perspective, these two technology are actually very compatible. They are solving the same problems with different tools. The traditional one, basically each word utilize a discrete representation. We call token. A word is a token, and then word and word, they are all discrete. The deep learning one is just fascinating. It turns out that we can actually transfer the discrete representation to a continuous representation in a high dimensional space. And once you do that, a lot of the things that you use discrete mathematical solve for can be transferred into this continuous domain and use more traditional calculus, tensor calculation. And so it's quite useful. So the like any NLP system, we start with a stop word model. A lot of words, you just look at their roots. That traditionally we use hidden Markov model for that. And once you have the subword model, you can actually build capture the longer distance of the words, how these units interact with each other to extract the meaning of it. And that's the what historically called n-gram. It's basically a Markov model. And then on top of the, once you have the phrase, then you want to know how the phrase are related to each other. And that's in NLP, it's called parsing. These are in NLP all different domains, but nicely on the in the deep learning world, it's all in the same framework. So it's very nice. But today we are in the data science, so I'll leave this aside, but focus more on the data part of it. But we do open one of the API in that. It's many people feel that it's actually the magical part of the deep learning in the sense that it can actually compare the semantic similarity between two arbitrary paragraphs and give you a quantity metric. So that is actually what we use in our system. It's a very atomic operation. You just put one paragraph on one hand and the other paragraph in the other hand. They can have zero lexical items in common, but we can actually compute how similar they are. And that's actually the one we use our machine reading nowadays to actually identify scholarly concepts in which field, so on and so forth. All right. So this is how the graph looked like. So this graph is already a little bit old, but in the center of the graph is the publication. So our first class entity is each individual articles. Each articles, of course, has authors. So you have multiple authors, and each author has a institution sponsoring their work. It's called affiliation. Each paper, we know that where we found them. So where they are, where it is publish, whether it's a special issue of a journal or it's actually a particular proceeding of a conference. So event is actually an issue of a journal or a particular conference instance, and the venue is basically this journal or the conference series. And on top of that, for each paper, we actually use the machine reading to identify the concepts and organize them into so-called field of study. Right now we have 50K, but the number actually is going very fast. This is this slide is only a few months old, but already the number of publication is above 170 million. So we already at 6 million papers on it. The biggest part of the graph, though, is not the entities. It's actually the relationships. The biggest relationship is paper-to-paper reference. We call citation relationship. And now we actually observe 3 billion citation pair, this paper cite this paper, but a lot of them we cannot ascertain the source of citation, so we drop that. And in the graph, we only include 1/3 of the citation. Right? So this is the graph. The graph is actually grow exponentially. So because this is based on the web crawl, everything on the web, we can discover them. And therefore, you see the articles going back all the way to 1870s. So you bet Albert Einstein is one of our authors. And all these Maxwell equation, all these famous people, they are here. And so this plot, what I'm showing you, is actually number of a publication based on the year, based on the publication year. And I want to bring to your attention that the vertical axis is in actually log scale. So this graph looks like linear. It means the number of publication is growing exponentially, right? It looks pretty linear with exception that, well, there's a dip between 1914 to 1918. That overlaps with World War I. And then there's another dip between 1939 to 1945-ish. That's World War II. And in between, in 1930s, there's flat. There's not much growth there. And it turns out that it's overlapping with Great Depression. So this graph actually tells us two things. Don't have war. War is detrimental to scientific development. The second thing is the scientific pursuit seems to be correlated with socioeconomic status. So when we see the Great Depression, there's not much growth there. The slope is changing rapidly, but in the 1970s, you see the slope is a little bit flatter than other. What happened in the 1970s? Oil embargo again. So it relates to the socioeconomic states. And after this graph is just zoom out a little bit, you see the slope actually tip up a little bit after 1994. What happened after 1994? World Wide Web happens. All right, so all this thing actually is faithfully captured in this. It's kind of fun. So the current growth rate, so you probably read a paper in Nature. Somebody actually did a study on the speed of publication growth, scholarly publication output. The 3 years ago, based on the journal articles, number of publication, it estimated that the scholarly outputs double every 10 years. Based on our data, it's actually already accelerated. Based on our data, it's actually 7.25 years. So it's going faster and faster. The two study has a very marked difference though. Our data, because it's web crawl, so we also include conference papers as well as preprints, whereas the previous study only looked at the journal papers. So that's probably a big difference. So I overlay this graph, I overlay the number of citations. I'm sorry? Oh, yes.
Is this a societal mark of the Western Hemisphere? Is that there seems to be a rise of the Good Friday and the Christmas holidays?
Every Christmas holiday?
Do figures every year?
Oh, the number of 10. So a lot of, we actually find a lot of journals, they actually, it's not, a lot of publications for, maybe it's our processing thing, it rounded up to the nearest decades. Yeah, so it's probably an artifact. Yes, yes, sorry, yep. And in terms of citation, similar, has a similar trend, it's also growing dramatically. It's suffering the dips between two walls. But you can, one thing you can see is the two curves are separating. The distance is bigger and bigger. What it means is the average number of citation references per paper is increasing. We have another report in this year's KDD. In the early days, each paper probably have 5 references. There will be the day, right? No reviewer will reject your paper because you don't have enough references. But recent year, if you do the math, on the average, each paper has 25 references. That's probably because the paper is more easily discoverable or whatever, or we are more collaborative. But it's actually a fun statistics. So again, it's also growing exponentially. So you can think about this graph. It's not a static graph. It's a dynamic graph. It's growing very, very rapidly. All right. So once you have this graph, as I mentioned, these are just a publication. You can also do the similar thing about number of authors and number of institutions and how do they collaborate with each other. I will refer you to our KDD paper entitled A Century of Science, how we actually report or how these entities are interacting with each other. Right. So let me quickly introduce, once we put a human readable interface to it, what it looks like. So it looks like a search engine. There's a search box in there. You go there, type in your query, you tell it what it wants. But this is an example of you type machine learning, all right? So if you try the traditional machine search engine, you type machine learning, you probably see a lot of result, introduction to machine learning, an overview of machine learning, so on and so forth. Basically, that's what today's search engine technology, it's keyword based. So it will try to retrieve articles that has the same keyword as your query. This one, because it's driven as a knowledge, what we wanted to do is actually better than that. We actually want to match the knowledge to your intent. In this case, the intent, when you type the machine learning, we teach the machine to interpret the intent as you want articles in the field of machine learning, not the article that has machine learning as keyword in the title. Okay, so it means that we actually, what it needs to be done is that you actually need to teach the system to understand the contents and then classify them into the right category. So this example, you type machine learning. The number one is support vector machine. It's a very commonly used tool, libsvm tool in machine learning. Even though in the title or in the abstract, it mentioned nothing about machine. It has machine, but it has no learning. But we teach the machine to learn them. This is actually a holiday, right? Because I see that there's no citation. Yes, that will be the bulk of the presentation. Yes, very good question. Yeah, so if you look at that, basically it's a semantic search engine. We try to understand your intent, and then you observe very keenly that the ranking is actually quite, it's different. It's not based on the citation numbers. I'm going to tell you how we rank. Yeah. Yeah, yeah. So there's a sort by, but there's something called what we compute as relevant. It's right. And on the right-hand side, that's the machine learning. That's the intent. We confirm this is intent. In fact, that paragraph underneath it is the paragraph we use to classify this paper as machine learning using the Similarity API. So it's kind of fun, right? All right, and so if you click on the one, if you click on the paper, I think this is the second one, which tells you the standard thing like abstract and how many citation it has received and so on and so forth. But we are teaching the machine to read, so reading the text is quite important to us. We are not only telling you how how many citations it is, how many references it made, or how it is received. We also try to extract the paragraph or sentence immediately preceding the citation. It's like the comment, the citing author's comment on the cited paper. And we feel that that comment is actually quite important, and we actually extract from here. It's hidden in a very obscure thing, but it's expert. So this is basically this author, David Lowe, citing this paper. And when you cite this paper, this is it's comment about this paper, right? Similarly, when this paper got cited by others, we also extract all the related paragraphs when the other papers making reference to this paper. It's like an anchor text on the web, right? So you can see how this paper got commented on the other. Are they flattering or they are criticism, right? So you can see all that. And last, we actually make recommendation related to say what other papers are related to this one, because we have a machine reading all the papers so they can compare similarity. And this is actually an interesting one. If you are working on a recommender system, this is actually very hard to do, in a sense that we are using so-called content-based recommendation. The recommender system tends to work well if you have user behavior. You know this user have clicked on this thing before. This is how Amazon works. People buy this, also buy that. That's behavioral data. In this case, we don't use click data. So the only recommendation we can do is solely based on content. So what you are seeing here is actually the machine reading results solely based on content and recommend related paper. There are a lot of surprises to me, myself. There are a lot of papers that it recommends are from the journal I never read, but it turns out quite relevant. So this is quite interesting. All right, so these are not only on after you type. A special thing that we put it in is that this agent is inferring your intent on every keystroke. So as you type in the search box, every keystroke is trying to interpret what you mean. And a lot of time, this is actually necessary because we as a human, we don't read as much as a machine. So we don't know. A lot of terms are actually quite ambiguous. By going through this large scale, we can actually do this. So for example, you want to understand what Microsoft work done in the World Wide Web area. You type Microsoft ... Did you know that ... have so many interpretations? It can be a World Wide Web as a field of study, which means the query means you want to know Microsoft's work in the World Wide Web area, or is actually a conference. So do you want to know all the publication of Microsoft in the conference? Or is also a journal, all right? And there are actually two of them. One is just called ... the other is World Wide Web Journal, right? And then finally, the ... can be actually a keyword in the title. You wanted to find some paper that has ... in the title, and that's actually one. So by using the semantic, we can actually do more. We can actually demonstrate what we are going to interpret your search intent as, and solicit your disambiguation effort right there. And so hopefully that will give you a better outcome. And here's the ranking problem, same thing. All these suggestions are actually ranked. So if you say, who are the expert in Microsoft about machine learning, when you ask this, suddenly it tells you a lot of authors. Now, of course, you can imagine when I do this, my machine learning colleagues will come and knock on our door. Why this guy is put it on top of me? And therefore, being able to explain the science behind it is very important, right? Do you agree? So let me tell you the ranking, answering your question. How is this ranked? So the exciting thing of this is we're using this as a way to see the machine in the process of reading. Can you also form the judgment on what are important articles, what are seminal work? And as a search engine, it has to present the result in an ordered list. So it has to learn how to rank them, right? So the way we are doing this, I mean, the nice thing about the scholarly field is we actually comment each other's work frequently in when we write our thing, we have to cite other thing and we put our opinion in there. So there's a crowdsource of a peer reviewed right there in the text of the publication. And therefore, what I show you, the citation context, they are actually super useful for these purposes. So we are basically using those citations as a peer review, as a form of a crowdsourced peer review, and try to infer what the importance as judged by the community in general. All right? So this is actually a large scale of assessment, research assessment. And using citations as a means of research impact is not new. In fact, this morning in a workshop, we talked about many ways. There are many ways of using citation, but all have drawbacks. Citation count, there are tons of indices that if you are not familiar, your advisor is probably very familiar with, like H-index or G-index to measure how productive as well impactful an author is, a scholar is, journal impact factor, how important a paper on a particular journal than the other one, so on and so, and the paper counts in the high impact. There are quite a lot of them, and Professor Ding is the expert, so you can actually take, maybe she has courses on that. But unfortunately, all this statistics are actually a proxy to something more important. And historically, these proxies were developed because of lack access to data. We hope through this, we can change that. All right, so what we did here, so how the ranking is done, we actually take a Nobel-winning algorithm in the social science that's in the economic world. They call it input-output equilibrium. In the computer science, you probably heard the later version called PageRank. So the differences between the just counting citation and this new way of work, this theorem is not all the citations are equal. If you are cited by a very important people, it's probably worth more than you are being cited by a lot of students, or no offense. Basically economy already figured it out, found out it's actually a better way to explain the nature of a lot of social phenomena. So the idea here is something called recursive importance principle. Basically says a research work is important if it is endorsed by another important research work. So the argument sounds like circular, but actually if you write it down as mathematics, even a simple linear model is actually very straightforward. Let's say the SI here is the importance of a particular article, and you can actually define the importance of the article is is a linear sum of the work citing it. So SI is actually just a summation of Sj, and then Aij is actually the degree of endorsement from the work J to node I. Right, so if you write it down like this way, it's very straightforward, linear equation, and you can write it in the matrix form that gives you the right-hand side, the lambda S equal AS. So this looks like a very straightforward thing, meaning that if you have A basically is the endorsement matrix. You go there to, for each pair of nodes on the graph, you figure out the strength of the endorsement and relation on each other, create this matrix, then you can solve the S, the importance of every node. This basically tells you that that node is just an eigenvector of this matrix, this endorsement matrix. So if those of a linear algebra, this is a good time to go back and brush your linear algebra. So it's very straightforward. And this idea is actually very old. It's 1904, before World War I. Unfortunately, this paper is written in German, So it didn't get widely discovered until very later in the United States. But it basically says that if this matrix, endorsement matrix, or in computer science we call it adjacency matrix, if this adjacency matrix is positive, definite, meaning every Aij is non-zero, then the importance vector has a unique solution. It's globally unique, which is wonderful, and more importantly, it has a great algorithm to compute them. And that algorithm basically is taking advantage of a fact in linear algebra that if it is dominant eigenvector, then you can actually start with any x, any vector, and you just keep looping it on them, and then it will eventually converge, regardless where you start. And so this can be implemented in a very scalable way called random walk. You just randomly select any node, and you follow the endorsement matrix to the next node, and then you count how many times a particular node is visited. And the fundamentally math guarantee that it will always converge, and whatever you converge will be unique as soon as the endorsement matrix get. A special case is that you normalize the endorsement matrix, so all the columns sum up to 1. And in that case, the endorsement becomes transition probability. How likely you are going from a node J to node I. So that's actually a very nice interpretation. And then the importance becomes a probability, meaning that if you randomly go ask your advisor for a paper to read, how likely a paper will be recommended to you. Right, so that's the importance. And the more likely the paper is being recommended to you randomly, signifies how important it is. All right, so these are actually very nice, and it is rediscovered in the library science to do in 1976, and then it got rediscovered again by Google guys, yeah, and they call it PageRank, right? But one thing that is hard for this math to work is the adjacency matrix or the endorsement matrix has to be positive, definite, or another way, the graph has to be strongly connected. In the real life, this is actually not the case. So in the real life, if you try to apply this, there's a problem. The nodes, all the papers are not citing each other, right? In fact, it's very sparse. The other problem that is new for citation is it's only one direction. You are not citing a paper in the future, right? So these are two problem things that run into this problem. So the PageRank people, the Google, when they started in 1998, they have a similar problem with a lesser degree. All the pages, they are hyperlink across each other. They don't have the second problem. The page can be updated to cite another page. So we don't have the second problem, but it does have this first problem, that the adjacency matrix is actually very sparse. So what they did is they introduced a teleportation mechanism. Instead of just following the endorsement, the hyperlinks, at certain time, there's some probability that you can actually teleport to everywhere you want, even to the paper in the future. So that's actually the contribution of PageRank. Just say, yeah, let's have all the paper connect to every paper randomly. And that makes the math work, so the random works. Unfortunately, it works well for web page, but it doesn't work well for scholarly publication. There's actually a study in Journal of Neuroscience. It's weird, right? Why this kind of paper is published in Journal of Neuroscience? But it's there, entitled Promise and Pitfall of Using PageRank for Scholarly Paper. And they found out that the original PageRank, they said this alpha is like 0.85, meaning that you follow the hyperlink for 6 times, and then you restart. In that one, they actually say, well, the alpha is more like a half, meaning you only read one journal, and then you start randomly start again. Kind of weird. And they also show a lot of evidence saying that it's very sensitive. What you end up with is very sensitive to that teleportation probability. So that's actually be the purpose of original idea. You want to have a globally unique, there's no wiggle room interpretation. This is actually not quite useful here. So how do we get over this problem? Well, the page rank and all these citation graph is based on homogeneous graph, meaning you only consider papers citing papers. What we did is we actually go through leverage the real graph, having the other types of a node on the graph. So if this paper doesn't cite the other paper, but there are other attributes, like, oh, the other paper is actually authored by the same guy, or they are actually published in the same conference or same journal. So you can actually have a relationship from paper to paper through different type of nodes. You can go through author, and then paper, or you can go to author, institution, and then paper, or you can go through journal and conference. So by richly leverage this different type of node, you can actually make the adjacency matrix among papers much more dense. And even though it's a lot of time is not good enough, what we did is this additional type, remember the field of study, we actually put keywords and field of study in salient keywords and study in that. So we actually, by doing all these tricks, we significantly increase the connection of the papers together. And so it makes the random walk work well without having to go through the teleportation. All right, so this is first one. The other one is, even we solve this, another problem is the paper, the aging of the graph. If you do this, the old papers tend to have more time to accumulate citations. So we found out that if you don't do the temporal correction, eventually the older papers would have more higher importance, which is not necessarily the right thing to do. So we actually introduced some aging. So the citation, we actually know the timestamps, and we let the power of the citation to decay over time. And so the paper has to remain to have a sustained new citation in order to maintain its influence and importance. And the model we use is very straightforward. It's a first order autoregressive model, meaning it's just decay over time. And by doing this, we actually introduce quite a few latent variables. And the way we actually learn these latent variables is to ask the machine to learn it by itself. And this is actually a feedback loop. So basically, if you think about what this is trying to do, the machine reader actually have work on the graph. It has some assessment of some ranking, and then you present this ranking to the user. But the user here are actually researchers. The researcher consume this recommendation of importance of papers, but they actually apply their judgment. And then when they write their articles, they don't necessarily follow what is recommended to them by search engine. And the good news is what they actually cite is something we can observe. So we can actually look at the observation and compare as what we would have recommended to them, compare the difference, and teach the machine to say, match that. So yes.
But to clarify, if I understand, you build the network not just by citations, but also by using these other variables?
Well, yes. Yeah.
So how do you build the edges? Do you have parallel networks that you can go for, or you substitute? You build an edge between two papers if either they're in the same institution or... Yes. So it's a heterogeneous walk. Yeah. Right. So because we can observe what user really cite, and so we can compare these, and then we train the system to actually adaptively learn those latent variables. And so the question is, how do you optimize it? The way we optimize it is very straightforward. We model this as a communication problem, information theory. The search engine is communicate what it thinks, the importance of a paper, and that message is communicated through some noisy channel. And at the end, we observe what is the user behavior.
that's how they cite. And so we communicate, we receive this. So this is modeled as noise channel problem. Therefore, we just use the information theoretical ultimate thing that what we want to optimize is the larger capacity. It's called maximum mutual information. It writes down to like this, and this happens to have a closed form. We can just optimize it. So this is actually a cycle. Like I said, every week we update the graph, we get the new citation and use that to readjust all these latent variable, and then the machine just keep churning on it. All right, so that's how the ranking is done. So what does it look like? Well, it turns out that it's these latent variables seems to be very stable, even though there's no theoretical or mathematical foundation to dictate so. The fact that they are, so it turns out that 80%, roughly 80% of the times, the citation, the paper-to-paper citation still play a dominant role. But the good news is other factors like author, affiliation, venue, field of study, and keywords, they're also playing some role. So when a new paper coming online, they don't have a citation yet, we can actually use the other thing to reach the paper and compute what is the implicit endorsement. The last one is the temporal, how quickly the citation power would decay. It turns out that it's an exponential model with half-life, roughly 6.5 years. All right, so, and the nice thing about this is they are quite stable, so it lends some confidence about the analytics we derive the data. Yes?
So can I interpret these implicit endorsement as a prior engagement?
Exactly, you're exactly right. So basically, yeah.
So on the previous page, did you also include like mentions in like social media, let's say?
No, not yet. Not yet. Yes.
I have to tell you, recently I get my knowledge on Twitter.
Yes. Yes. So there's another effort called alt metric. They try to include the additional citation, but the framework is very straightforward. You can just add them as a publication. Then you can estimate the reputation of an author. Twitter just becomes a venue, and it fits right in. It's just another type of nodes you can add to this already heterogeneous network. Right. So the difference between this work is basically it try to weight each endorsement. Remember, there's AI. It try to weight endorsement, but the most a very common way of in the field is just count citation. Treat every citations as equal. So how different are they? Well, we do the ranking exercise to study what Santoyo observed. If we have a lot of queries, we look at the papers and we rank them using citation counts or ranking them through what we call saliency, this new way. How actually agree how much they agree with each other. It turns out that the major role means that the paper position are ranked identical. It looks like the major activities are there, but you see there's a lot of spread, meaning that there are quite a few situations they do disagree, and that's actually a plot. So only 20% of the time that these two metrics will give the paper the same rank position in the search outcome to the same query. You have to go to the 9th position to get 90% agreement. So you allow the rank position to be different by 9 positions, then you can have a 90% agreement. So citation and weighted citations, they are very different. All right. Yes. So the funny thing is, once you have this importance on each individual article, each paper, then you can actually use this to infer how important their affiliate associate entities are, like how important the author, by aggregating all the papers they have published. And there's actually a nice way. You remember the importance of the paper. Each article is actually a joint probability of not just the content of a paper, but also who wrote it and which institution sponsored it, so on and so forth. So it's actually a joint probability. So if you want to know how individual author, how important it is individual author, you just take this joint property and marginalize the distribution. So if you remember the search engine, not only it actually tells you the paper, but it also tells you who are the important author, what are the important venue, and this is actually computed this way. Those results are computed this way. And so we actually can derive a lot of metrics and compare it with existing metric. The first thing we try, of course, is author, because people care about their ranking. So we actually take the way we compute the author is by looking at all the papers they published or as a co-authors and sum up their saliency. And then we compare it with H-index. And this is the result. It looks like the H-index and the saliency seems to be agreeing to some extent because you see the trend right there, but you see that disagreement is also large. The one I actually want to highlight is this poor guy that has H-index only 11, which is quite low. But in the next slide, I will go to tell you that's actually a mischaracterization of that poor author. And on the other side, you can see a lot of H-index, a huge H-index. Do you know who they are? They tends to be famous, no offense, I'm here to offend first students, not offend professors. Those people that have high H-index tends to be professors having a lot of students. Right? But that's probably well deserved because they actually cultivate a lot of students. But the one case, the H-index 11 one, we actually double check with the data. It's actually unfortunately the case because in many research world, like especially those of us in the industry, we actually focus more on quality than quantity. So we don't write a lot of papers, but we want to make sure our papers are very influential. That person, H-index 10 or 11, actually it has accumulated citation. This is actually coming from Google and from us. Has accumulated a lot of citation, meaning they are impactful. So H-index is actually a very horrible, metrics to evaluate a person, the product, all right, unfortunately. But now we have a better thing. That's the thing. Right? Another point I wanted to make is because the derived entities, they are actually a summation, so the number actually counts. So there is two notion, prominence. You can actually achieve a lot of, you can be very important by simply having a lot of work, but on the average, most all the work are just average. Or you can actually, like the H-index 11 person, you don't do a lot, you don't publish a lot, but you actually make a lot of impact, and we call that prestige. All right, so on the average, what is the hit rate of everything? And so this is actually a study we do with DoD on the computer security area. They ask us to rank conference or publication venues. And so there are two ways, two axes. One is based on prominence, that's the horizontal one. The ranking one is on the upper, on the right. So, and the other, the vertical axis is normalized, size normalized. Ranking is the prominence. So the top ranking is on the top. So to the upper right is better. And it turns out that even though this is a computer security, the surprise to the study is, wait, a lot of security conferences showed up here, but there are also other conferences showing up here. They are not traditionally considered as security conference. The NDSS, for example, is an operating system. CHI is a computer human interaction. It's UI conferences. The nice thing about this is when you have this unintuitive result to the so-called expert in the field, you can go back and look what papers are included and read them. It turns out that a lot of operating system papers, they are talking about security of operating systems. About the CHI paper, human interface computer, they are talking about how easy the UI implicates the password is horrible and the interface is wrong. They are actually legitimate computer security paper. So what it basically tells is we are having a new way to ask different questions. Traditionally, the question we ask is what computer security conferences are publishing good paper? So you already classify publication venue as particular field. Whereas this one, we can ask the different question. What conferences are publishing good security paper? Right? So they are actually very different. That's why you have Chi and all this other here. Right, so without a article level assessment, this answer would be hard to answer. And we hope that this data sets can actually bring the new way of answering this question to the world. Another common practice is we say, yeah, congratulations, your paper is published in this prestigious journal or conference, so you should be awarded. There's actually Nature article saying that how Chinese institutions, Chinese scholars get rewarded every time they publish a Nature paper. A lot of real money. Is that a good practice? It turns out it's no. This is actually just individual paper published in the same conference, and we look at their importance. It looks like it turns out that there's actually widespread distribution. So a top tier, the top tier conference and the mid tier conference, they actually have a lot of overlap, meaning the top paper in the mid tier conference can be actually better than the less influential paper in the top tier conference. So this is actually a good message to send to these funding agencies or government agencies. Please don't use that way it's a wrong incentive. Don't use that way and now we have a scientific data to back it up. All right, so this is just for fun. Last week, there are a lot of, recently, a lot of university ranking things showing up. So I just think that for fun, I'm doing my university ranking. This actually takes one API call in the thing, and we can do it on a weekly basis. Every week, we update a graph. We have a new university ranking, as opposed to the university ranking is only annual efforts. But the key point I want to emphasize is the university ranking is probably painting the picture of university in too broad a stroke, because this is the ranking you see Google, MIT, and things like that in CS. Once you go to AI, suddenly a lot of universities disappear, but a new university showed up as prominently. This shouldn't be a surprise, because university have their actually emphasis area, different focus area. So if you just say this university is better than university, it's actually very misleading. You need to be more specific in terms of which program are you talking about. So AI is a subfield of computer science. You already see this a lot of, if you compare these two charts, they are already very different. Let's zoom into a subfield of AI. In computer vision, you see even more differences, which means that even a field of AI is already too broad. So another way to say this, well, it used to be very hard to get this kind of in-depth understanding about institution. Now we have a article level assessment. You can aggregate. Hopefully it can give us a better picture. All right, so I'm already run over time, but this is a summary of what bring to the table to the community. We encourage everybody to give it a try, give it a look. And here is some examples for institutions that are already using it. This one, this one called Open Academic Graph. It's from a loosely connected group of us that are interested in doing studying of this paper. And Microsoft Academic Graph is proud to announce that we actually work with Tsinghua University, who has a separate academic graph called A minor. And recently we just merged these two graphs together. So our graph has many English contents. A minor has a lot of Chinese content, so it's great, complementary to each other. Yes?
I was just asking if there are any problems with the merging.
If there,
Issues when you try to merge it.
yes, disambiguities and all these things, right? Yes. So this is a research topic, very tough one too. And this one is actually a visualization effort. So anyone doing big data visualization? Maybe not, but this is actually a hard one. If you have a big data, how to visualize it, how to use it efficiently is actually very hard. This one is from Jiao Tong University, Shanghai Jiao Tong University. It's also hosted in the Open Academic website. All right, so we are looking forward to answer your question and to provide more assistance in case you find this data sets interesting. And we hope that in the near future we can see your collaborative outcome there, and we can actually point the attention to your research work. So with that, I'm sorry I'm 5 minutes overrun. I'll be happy to answer questions. Yes.
Great talk. I now understand a lot more about what's going on beneath the scenes. So my question is, this graph you produce is homogeneous and weighted, and assumed by the NLP machine reading results, right?
Yes.
But you also mentioned later on you use these
Deep learning.
deep learning to learn the weights. So how do these two fit together?
So in the end, the traditional NLP and the deep learning based one are both trying to assess probability of the observation given model. So when you unify at that mathematical level, they are actually quite compatible.
Interesting.
Yes. Yes.
So a couple of questions. First of all, I'm looking for the link where I can get the API. Is that on azure.microsoft.com and then
/in. Yep, and then academic knowledge API. Yes.
And then the question is, so what's your model how do we get in, right? So to learn how to use it and start using it for our research.
Yeah. So
there's some pricing involved also.
yeah. So the Azure one is hosting in the cloud, so you can write API to access cloud. But our friend at Tsinghua, they actually take a dump of it. So if you go here, there's a link somewhere here. You can actually take a dump, a snapshot of the graph. It's
but if I wanted to start piloting stuff from here, would I apply for an Azure credit?
Yeah, you can.
That's all I need.
Yes.
Apply for an Azure credit award and then start using it.
Right. That Azure thing actually has this free accounting. Like the first 3 months, it's free for you. Yeah. Yes.
I'm just curious.
Yeah.
I may have missed this, but like the graph you showed the rankings by university or industry.
Yep.
Companies by like subfield. Do you rank authors that way as well?
Yes, you can do it
Is
today.
that available to us to go?
I encourage you to do it. Seriously. All this chart it takes only one API call.
Okay.
I'm not kidding.
I'm
Yeah.
thinking of like trying to find the experts in your field.
Uh-huh.
Like, oh, who should I follow?
Yep. So your query is field of study even equal to this field, and give us the ranking based on authors.
Sorry to interrupt, but did that query give you the, so it's a result of both NLP and the page rank?
Yes. Yep.
The end result of that.
That's right. Because the query is field equal to, let's say, machine learning. So you have to actually read the papers to classify them as machine learning, even though the whole paper has no machine or learning in it, right? And then once you gather all this paper, he wants to know the authors. So you do treat all these individual papers as joint probability and then marginalize based on author.
So if I understand correctly, then it's like take the dump here, which is sort of the backbone of what's done on top of that.
Right.
So let's see what's the difference.
So the dump there, each paper should have a very mysterious field called log likelihood.
Okay.
That's that. So it's in the log scale. Yeah.
Do you have any idea of how to validate the ranking? Because the ranking is just a recipe.
Right. So we use this. So we actually consult our internal experts. We run a ranking exercise. This one is a real project. So Microsoft have researchers serving as a consultants to a major funding agencies in computer science area, computer security area, and they have an expert-based ranking, and we have a machine-based ranking, then we duke it out. This is your ranking, but this is our ranking. So what are the difference? And we dive in, I say, wow, I didn't know that mobile network has so many security papers. Then you think about it. Of course, mobile you have to consider about ranking, right? So we actually run a lot of exercises inside Microsoft Research. And so all the examples you see are based on the computer science area because that's the area we are more familiar with. And I'm eager to hear people from other fields like physics or biomed to tell us how good this ranking is. Yeah. Yeah.
Can I? Or you want to go ahead?
Oh, right.
The data set of MAG is such very huge data set.
Yes.
Cover large amount of papers.
Mm-hmm.
So I was wondering, have you explored the different disciplines of the data set? Or as we can see the instance examples of this.
Yep. So so it's a query, right? So you found a small subset, you just base your query. Let's say you only want computer science. You just issue a query, field of study equal to computer science, and what it gives back is a subgraph of all the computer science. Yeah. Yeah, we have a 50,000 field of study. Be my guest. It even has family law. Like one of the authors in the graph is Barack Obama. What? Barack Obama is here, but actually he wrote JAMA paper. Journal of American Medical Association paper, seriously, and Hillary Clinton is also on that. They're talking about health insurance, health policy, and he published in top tier medical journal. Yeah, and so you can go there and do all sorts of things. Family laws, people want to know grandparents. The affiliation is, no, I don't remember. Yeah, some of the maybe has no affiliation, yeah. Yeah, so Barack Obama is affiliation U.S. Senate. I think he wrote the paper as a senator. Yeah.
How do you handle author name design?
Good point. So heterogeneous graph. So we see the author and we look at the all other, so if the author, we look at co-authors, institution, and the topics, the field of study they author, and the conferences and journal they publish. And so we train a model based on that. So that's why currently we are at the curve precision recall. We are actually doing very conservatively. So we want to run the risk of conflating rather than over-conflating. It's actually harder when you put two people together under one node than just let people say, yeah, these 5 nodes are all me. Right. So what I didn't say is this second version, we actually have a sign-in option. You can go in and say, well, these 5 different authors are all me. There's a claim facility there. Currently, we know we are heavily under-conflating, but that's by design.
So this 170 million article you released, treat all the author name as plaintiffs and beautiful.
We actually have a hypothesis. Yes, we assign all the authors to a cluster, to an author cluster. So this authors cluster, we are sure these papers are actually by the same author. But we are not quite sure is this author class, like author cluster, they are not from the same person. We are not quite sure that, yes. So we hope, currently the author numbers, we actually tune the threshold a little bit. Now the unique author cluster are actually 133 million. We know it's overestimated because we are a little bit conservative. So we are hoping people please sign in and claim your papers. And then that claim signal would be a supervision signal for our machine learning to learn. Yeah.
You actually have a Google Scholar which people really claim.
Yes.
As your country.
Right. The problem is Google Scholar, people can ask Google to automatically add papers to it. And it works horribly for Asian names. Yeah, Google is doing opposite. So they actually run the risk of over-conflating. So they actually assign, if the name looks similar, they assign it to you. Yeah, so we are on the opposite way of the philosophy. Yes?
So suppose we have paper A,
Mm-hmm. Mm-hmm.
can we get all the citation context of paper A?
Yeah, so for...
And also be the network.
Yes, so for the papers we have access to the full text, and the publishers didn't prevent us from distributing that information. Yes, we have. Yeah, and typically those are from open access journals or the online articles.
We have a paper published in PLOS, right?
Mm-hmm.
So can we get all the citation context
Mm-hmm.
of this paper?
Yeah, depend on the citing sources. People who cite you, if their publishers actually allow us to distribute that information, it will be there. Mm-hmm. Yeah.
I wonder how you guys are dealing with longitudinal data, like author change affiliation.
Yeah. Yes.
And like new citations.
Mm-hmm. So for a while, we actually use linking data. So we know this person moved from this organization to the other organization, and then we realized that we actually have more people than linking.
So
Yeah.
actually bought linking, right?
Yes. Yes.
So you're saying in the graph, we can actually go to say, from this year, he's living with that, and that year.
Yeah, but then it's not lined up very well. A person can change job in this year, but his paper showed up 2 years later. Yeah, so it's not lined up very well. So that's why we actually tune the threshold, because now we are actually asking people to help us. We allow people to sign in and actually make the correction themselves. Mm-hmm.
What is the relationship between this academic graph with linking? Also recently announced the economic graph.
Economic graph is linking.
Yeah.
Yes.
So do you have some connections? Or
We're trying to work together, but like I said, we actually try to, and linking is author-centric, right? We are actually paper-centric, right? So we try to actually do an intersection on how many people we're overlapping. Surprisingly, it's not that many. Yeah, only computer science people are there. Very famous professors, they don't bother to have a linking profile. That's one thing. And non-computer science or computer engineering, like a lot of physicists, a lot of biomed authors, they don't even bother to create a linking profile. Yeah, so the overlap is actually not high.
for the visualization, you say there's a large waste. Did you try large waste due to the kind of like Chao Rumei did that?
Yes.
I'm curious.
I'm pushing them. So our data set is really, really huge. So almost all the visualization tool we know cannot handle the data at this scale. So you basically have to push them to do multi-resolution kind of visualization, and that's a virgin territory. So interested in going invade the CHI? Good opportunity. All right, thank you very much.